Hello everyone. So in this video, we'll talk about how to use the software moves to solve for the temperature profile in a UO2 pellet. So in this case, you will be given an input file and you just need to run this input file. We'll talk about how to modify it also, but basically the main structure of the input file is given and you just need to run the input file, and then we'll talk about how to visualize the result and how to understand the result. And then also a little bit about the, the background and the physics of the problem, and also about how to modify the input file so we can run a couple of simulations to do some kind of parametric study and understand how changing some of the material properties change the output, and how does that basically uh, demonstrate our understanding of the physics of this problem. So how to do that? So basically, a little bit of background first. So there are three different main modes of heat transfer in materials. So we either talk about conduction, mainly in solids, and that depends on the type of solids. So basically, the heat carriers under the conduction mechanism could be either electrons, like in metals, or phonons, like in ceramics. Or if we're talking about fluids, then the main mode of heat transfer will be convection, or at very high temperature, like with black body radiation, at very high temperature, also the basically heat transfer by radiation could be an important source of, or an important mode of heat transfer that we should consider. However, in most cases, and especially in solids, we are concerned mainly with heat conduction. Again, depending on the type of solid, so whether we are talking about metals or ceramics, then basically the heat carriers would be different. So in metals, the heat conduction is mainly dominated by electrons, are the main heat carriers, while in ceramics or insulators, then we have basically those vibrations. So those phonons are basically the quantized energy version of heat, and basically as opposed to metals or electrons can move from one place to another, and that's how you transfer heat from one location to another. In ceramics, because electrons are localized, the heat transfer just basically through simply the vibration of the atom. So it's basically from one place to another through the collective vibrations of atoms. And the quantized version of those vibrations is what we call phonons, similar to basically when we treat light, and basically we call the quantized version of energy as photons. So what types of laws and equation we use to study heat conduction in solids? So basically the most important material or constitutive laws that we use is basically Fourier law, which tell us that basically the heat flux is linearly proportional to the temperature gradient. So depending basically on the gradient of the temperature, so the heat will transfer from basically high temperature regions to low temperature regions. So that's where this equation come from. So if you're not familiar with gradient and fluxes, that's fine. We're gonna solve it in 1D anyway. But basically, this is the generic form of the law. So Q here is the heat flux, it's a vector. And basically the gradient of a scalar function give you a vector. So the gradient is basically a vector that points to the direction of the increase in this function. So the gradient of the temperature is in the vectors that point to the direction of the increase of temperature, and the flux is proportional to the negative of that gradient, meaning the flux will go in the opposite direction. So the flux of heat goes from high temperature to low temperature. And this is a very common form in constitutive or material laws. So this is basically has to do with the fact that those are the simplest forms of constitutive laws that we can introduce that follow or don't violate the second law of thermodynamics. So the simple 1D version of that in a Cartesian geometry would be basically the x component of the flux vector would be proportional to the first derivative of temperature in the x direction. Now, an important observation that we can make based on that law is basically first that basically the higher the conductivity, the more efficient the extraction of heat from material, because you can get basically more flux for the same temperature gradient. On the other hand, if we are talking about the same flux as an input, this is the flux, like in our case in nuclear engineering, this is the flux, the heat flux from fission, the generated heat flux inside the fuel. So the higher the conductivity also mean lower the temperature gradient in the fuel. And that's very important as we're gonna discuss in a minute, because temperature gradient lead to a phenomenon that we call thermal stresses. And if you have very high thermal stresses, then you can basically fracture or fragment the material. And that happens very often for ceramic fuels like UO2 and for ceramic materials in general. So we need in many applications where we want to basically benefit from the heat generated, from the heat that is generated when we want to extract more heat, it is of course important or beneficial to utilize materials with high thermal conductivity. Now, if we have heat generation, then basically the Fourier law is what we call a constitutive law, but to solve for the temperature under different conditions, we use basically a balance law. So in this case, it's the balance of heat. So heat is a form of energy, so energy is conserved. So we use balance laws to basically see how things are going to conduct or diffuse, while basically at the same time accounting for the fact that energy is conserved. So the balance law would look something like that. It's basically a partial differential equation. So in addition to those gradient and second order terms that represent the conduction or the diffusion of heat, we have basically the left-hand side tell us how heat will change with time. So this is basically the time derivative of the internal energy. And if we assume constant density and heat capacity of the material, then this becomes simply the time derivative of the temperature. So the temperature will only change because things are diffusing or conducting from one place to another, or if there are a generation, a source term inside the material. For example, in our case, in nuclear engineering or inside the fuel, this is because of the fission events that are happening inside the fuel. So if we basically assume constant thermal conductivity, then this divergence and the gradient term simplify to just a second order derivative of the temperature. We basically take the temperature outside of the derivative, the thermal conductivity outside of the derivative. So this term also, if you're not familiar with, that's fine. It's called the Laplacian. So this is the second order derivative in the three directions. We're gonna solve the problem in just simply 1D here, but we use the gradient and Laplacian because those have the same meaning and the same formula regardless of the geometry of the problem. So this, we can write the law in this form regardless of we are going to talk about it or solve it in Cartesian geometry or spherical geometry or cylindrical geometry. And then this is basically the volumetric heat generation rate, meaning it's heat generated per unit volume, per unit time, or per meter cube per second. So if we basically kind of lump those terms together, constant of the material properties, basically the density, specific heat, and thermal conductivity that give us a one parameter that's called the thermal diffusivity. So this we can divide the equation, and basically we have just the thermal diffusivity, and that shows basically the similarity between heat conduction in material and mass diffusion in material. So the thermal diffusivity would be the analog of the diffusion coefficient in diffusion problems. And similar to diffusions, then we'll have basically a diffusion length or a conduction length in this problem. And we'll have also characteristic time scale. It's the time scale that represent how fast or how slow things diffuse. So this is related to the length scale and to the thermal diffusivity of the material. So this problem in general, it's a transient problem, meaning it is function of time. As the left-hand side is just the time derivative. But if we're just interested into the steady state solution, meaning the solution at basically long time scale, then basically we can look at the solution of this BDE when the time derivative goes to zero. That would be the steady state solution, meaning this is solution at longer times, and also this is the solution that is no longer dependent on time. So it's time independent. And this problem could be even simplified further. Of course, if you don't have any generations, then it becomes basically the second order derivative just equal to zero. And if you're solving in 1D, then this becomes a simple ODE, right? Ordinary differential equation. It's no longer a partial differential equation if it's just a 1D problem, a 1D steady state problem. And for simple geometry, that's basically if it's a slab geometry or using Cartesian coordinate, have just X component, then the solution to this problem would be just a linear profile. If it's, again, if there is no generation, there is no heat source. And also this basically Laplacian term, this generic second order derivative will work for also different geometries. So it would be the same second order derivative in terms for cylindrical or spherical geometry. And if we assume just radial change, there is no basically angle dependence in the change, either cylindrical or spherical geometry, or axial dependence for the case of cylindrical geometry, then we will also have a simple, basically second order ODE that we can solve, and depending on the boundary condition, we just need to integrate twice and apply the boundary condition to get the analytical solution. For the case of Cartesian, this is very straightforward. It's just a linear profile. However, of course, in many cases, like in the situation that we are discussing here, we have a heat source. So under, of course, fuel pellets and fuel rods in reactors, they undergo fission and they generate heat, and that's how we extract this heat and use it to basically generate power. So in such condition, we will solve this. It's still ODE if we're looking for the steady state and if we're assuming spherical symmetry, so there is only change in the radial direction. So in that case, basically it is still a relatively simple ODE, but we have a source term. So to solve this problem, it is still relatively straightforward because we just need to integrate twice as long as we're assuming constant values of the heat source and the thermal conductivity. However, that's of course not very accurate, but we can, just for the sake of simplicity, we can take average values of this. So the thermal conductivity depends on the temperature, and especially under irradiation, of course, there is material degradation under irradiation because of irradiation effects. All of those defects that are generated will reduce the thermal conductivity. And we're gonna relatively basically account for that indirectly by changing the value of the thermal conductivity. And also for the heat flux, there is some radial dependence because of basically uh, the fission product and the plutonium and the self-shielding, which is related to the neutronics of the problem. However, we can ignore that for simplicity and take an average values of the heat generation and the thermal conductivity. If we do that, we can actually derive a simple analytical solution that we will use to demonstrate or confirm or validate the MOS solution. So the MOS solution is a numerical solution. It uses the finite element method to approximate the solution of the partial differential equation. However, to validate, to make sure that things are implemented correctly in MOS and we are using MOS properly, we're gonna solve this relatively simple problem using MOS and compare the numerical solutions that we get from MOS to the analytical solutions that we know it is correct and exact. So the analytical solution is simply a second order profile that we call a parabolic profile here, that is basically tell us that the temperature at any radial position, T as function of R, is dependent on the temperature at the surface or at the edge of the pellet, the fuel pellet, and it is dependent on the amount of heat generated, of course, inversely proportional to thermal conductivity. So if you have low thermal conductivity, then the temperature would be higher. And then it depends also on basically the radial position in a second order or in a parabolic manner. And also this solution give us this simple relationship that basically the center line temperature compared to the surface temperature, so the periphery or the edge temperature of the pellet is simply proportional to the amount of heat generated and the radius of the pellet and inversely proportional to the thermal conductivity of the material. You can also derive an expression for the flux at any position. So this is just the gradient of the temperature multiplied by thermal conductivity. So that will give us a function only that depends on the radial position and the amount of heat generated. And then at any, if you calculate the flux at basically that is generated or that is extracted from the surface of the pellet, would be just dependent on the geometry of the pellet. So it's the amount of heat generated per unit volume multiplied by basically the volume of the cylinder. So just to give you a brief reminder of the different scale and the geometry of different things inside the core. So basically the pellets that we are going to be solving for the temperature profile in is basically a cylindrical pellet with diameter of about 1 centimeter and height of 1.5 centimeters. So this is just one UO2 fuel pellet. We bought hundreds of those pellets in a fuel rod that has almost the same diameter, but it is about 3.5 meter long. Then about 200 of those fuel rods, we bought them in a fuel assembly. And then we bought also about 200 of those fuel assemblies inside the core. And then the core itself is inside a bigger pressure vessel. So back to the material properties that we call thermal conductivity and to the specific fuel that of interest to us because it is the main commercial fuel for nuclear reactors is UO2. So UO2 is a ceramic material, right? So it has a lot of advantages and that's why it has been adapted for all those years or decades in for different types of cores, mainly light water reactors. And basically, because of the fact that it has high melting point, it is chemically inert, especially with coolant like water. But it also has this nice fluoride crystal structure, which basically has relatively some open space that can accommodate some of the fission products that appear after fission, which lead to basically better tolerance or better radiation resistance of this material to or under service or in operation. And also it is a single phase material. It is has this fluoride crystal structure all the way up till melting, so it doesn't change phase like other materials that could change phase with temperature. And that also has beneficial aspect because that means there will be no stress generated during those phase transitions that could happen in other materials. However, because it is a ceramic material, so it has a few shortcomings. And that's actually one of the main area of research now, or the main reason driving or motive driving the research to either improve U2 by doping it with other materials to increase its thermal conductivity or to utilize different types of fuel. And that's because of those shortcomings, which is the one that's very relevant to our talk today is the fact that it has low thermal conductivity. So that means it's not a perfect candidate or a choice for heat extraction, as we said before. And also that means it will lead to cracking and fragmentation because lower thermal conductivity means you will not efficiently extract the heat, so the temperature would be high, and the temperature gradient between the pellet center and the pellet edge would be high, and that will lead to high thermal stresses, which eventually basically fracture those CO2 pellets. So again, the thermal conductivity is actually has a complex dependence on temperature for UO2 and even more complex dependence on radiation. Basically, for the sake of simplicity, we will just ignore the fact that thermal conductivity will change with temperature and time in reactor, and we're gonna just take average values to represent basically either different temperatures or different stages of life in a reactor. Again, that's the main issues with UO2 fuels, and that's why there is a lot of interest and research now in improving those fuels in different ways, either by just adding dopants or by using different forms of fuels like metallic fuels instead of ceramic fuels. So it is the fact that the thermal conductivity is low and the thermal gradient is high that we have those kind of fractures that appear in UO2 or uranium plutonium oxide, which we call the MOX fuels. So the problem that we are solving is the same that we just mentioned. However, here it's just taken directly from basically a nuclear engineering textbook, and we're gonna go over a few of the nuclear engineering definitions and calculations. So the problem itself is exactly the same. We are solving for a steady state profile, so the time derivative equals 0. We have a source term here that's Q of R, but we're gonna approximate it as constant later. And then we have this second order derivative in the cylindrical geometry and assuming just radial dependence. So the problem itself has different mode of heat transfer. So basically there is heat conduction inside the fuel, and there is usually some gap between the fuel pellet and the cladding at the beginning of life in reactor. That's to allow for to allow some room for swelling, because we know under irradiation they go to swell. And also there is heat conduction in the cladding itself, and then there is heat convection in the coolant, and there is this boundary between convection and conduction between the cladding and the coolant. However, for the sake of simplicity, we're only talking about conduction inside the fuel, and that's where this equation is valid. So we are going to assume that we already know, so we already solved the heat transfer problems outside of the fuel pellet, and we know exactly what is the temperature at the surface or at the edge of the fuel pellet. So we only need to solve the conduction from the pellet surface till the center line of the pellet. So to do that, we need to basically calculate this source term, the heat generated from fission. So this is related to the amount of energy released by fission, and that's this familiar number that we use. It's about 190 MeV. Sometimes we use 200, but there are 10 MeVs that are lost to those neutrinos. So because of that, this is the conversion factor just from MeV to Joule. And basically, now the only unknown is the fission rate, and the fission rate is basically dependent on the operating conditions, the reactor, and the fuel. However, the number for light water reactors are known. It's about 10 to 19 fissions per meter cube second. And this number would be given in the input file, but basically this is how we use nuclear engineering calculation to calculate this heat generations that we use as a source term in our equation so it's an input in that input file. And this is also related to some another important nuclear engineering concept or definitions that we use a lot, that's called the linear heat generation rate. So this is basically, again, we know the fuel rod is a cylindrical tube, so you can get an estimate about basically how much power is generated per unit length of that tube by just simply multiplying the heat rate or the heat generation by basically the area of that pellet. And those are our boundary conditions. So we know what's the surface temperature of the pellet, and we know that at the center of the pellet, basically the temperature gradient would be 0 because of the fact that this would be the maximum temperature. So that it's going to be a symmetric profile with respect to the radius, and the maximum of this profile would be exactly at the center line of the fuel pellet. So based on those conditions, again, similar to the analytical solutions that we have seen before, so it is exactly the same analytical solution, except here we are using basically the nuclear engineering definition and parameters. So basically, the solution is again parabolic or second order in the radius, and it depends on Q, the amount of heat generated, the radius of the fuel, and the thermal conductivity of the fuel, which you can also transform that into a linear heat generation rate. But basically, this is, as we will see, and when we look into the input file, this is basically the analytical solution that we will compare against. So we can actually type this analytical solution inside the Moose input file and ask Moose to take the difference between this exact analytical solution and the approximate numerical solution that Moose calculate when we run the simulation or when we run the input file. So of course you can solve this also in different geometries. You can solve it for a plate-like geometry, or you can solve it for a sphere geometry. However, for the cylindrical geometry that we're interested in for the pellet, another also important, well-known outcome of that parabolic profile is if you calculate the average temperature. So we have the center line temperature, we have the edge temperature. If you calculate the average temperature per pellet, so because of the fact that this profile is simply a second order, a parabolic profile, if you integrate it over the volume, you get basically a arithmetic average as your average temperature. So the average temperature, so if you want to assign an average temperature, because the temperature change from the center line where it's maximum to the surface or the edge temperature where it's minimum, and this change is parabolic. But if you want to assign an average temperature or talk about an average temperature, you can do that by basically calculating the average by integrating over the radius. However, because this profile is simply a second order, if you do this integration, you end up with a simple formula which is telling you that the average temperature profile is just the arithmetic average of those two temperatures, the T naught, the center line temperature, the maximum at the center, and the TS, the surface temperature, which is the temperature at the surface or the edge of the pellet, which is basically known, this is our boundary condition. So this is known, this is given, while the center line temperature is what we solve for, what we calculate. So in general, if you look at any nuclear engineering textbook, the solution will look something like that. So basically, again, there are different modes of heat transfer. Actually, there is heat transfer by convection in the coolant. That's where we calculate the T coolant until it reaches the cladding. Then there is heat conduction in the cladding. And then depending on the gap, so initially, if there is gap, this gap will have helium gas. So it will have very high thermal resistance. So that's why there is a big jump here in the heat because of course there is the conduction of heat in that gap is very limited or very inefficient and the temperature is initially high. However, once we close this gap, so as basically fuels continue to be in operation, the UO2 will swell because of irradiation effects and basically it will close this gap. And in this case, there will be better conduction and that will drive the temperature profile down. So basically, you will see an improvement in the conduction. The jump here is not as high as initially was. And even the center line temperature will be lower once this gap is closed. But what we are solving for is this temperature profile inside the fuel pellet. So we are assuming that we already know the temperature here, right? And we're assuming that gap was closed, so we know the temperature here, and we just basically, or actually here, we know the temperature here, and we're just solving the heat conduction to get this profile inside the fuel pellet and to get this maximum center line temperature. Of course, you can see that this problem is central to the safety and performance of fuel and of course the entire core or plant or power plant because of course you want to make sure that temperature is not high enough to melt the fuel, which is usually a very extreme situation, but also you want to make sure it doesn't melt a cladding or it doesn't lead to what we call the breakaway corrosion that happened to the cladding, which, for example, happened in the Fukushima accident, because this breakaway corrosion gave rise to excess hydrogen gas, and then hydrogen gas could lead to those explosions inside the core. But knowing the temperature everywhere from the coolant to the cladding to the fuel is of course a paramount to the operation and safety of reactors. And for the case of the fuels, that also lead to the cracking and fragmentation of this fuel pellet. This actually happened even during the startup of a reactor because UO2 is very brittle material. It's a ceramic, and because of this high temperature gradient, we get thermal stresses, and those thermal stresses lead to fracture because the thermal stresses are usually higher than the fracture strengths of UO2. And we're gonna have another video when we make those mechanical calculations. We calculate the stresses based on the temperature gradient. But for now, for this talk, we are just calculating the thermal performance and not the mechanical or the coupled thermomechanical performance, which we will talk about later. But again, that's basically the reason for all those cracks that we see very early on. Things, of course, become worse in operation after a few cycles and definitely towards the end of life in reactors. So again, we are just solving the heat conduction equation in a cylindrical geometry or assuming only radial dependence and constant heat generation. And then we are looking for the steady state solution. So this time derivative becomes zero, and then this becomes an ODE. So it has analytical solution as we discussed before. So the problem statements that we basically are going to solve, and that's we will see those numbers inside the input file when we look into the input file. So we are basically assuming the radius of the pellet to be about 4 millimeter. We're assuming the thermal conductivity to be constant of 5 watt per meter Kelvin. We are calculating this heat generation rate again based on the fission and the energy per fission. And we're assuming this surface temperature, the temperature at the edge of the pellet, to be already known and equal to 700 Kelvin. So what we are going to do is basically to utilize that we are given an input file that's ready to run. So we are going to run this input file and run the simulation and calculate the temperature at the center line, calculate the average temperature, and compare that with the analytical solution, and ask Moose to basically calculate the error. And the error is defined as the L2 norm, which is basically the difference between the analytical solution and the numerical solution summed all over the elements, where we are taking basically the square of the difference, so that basically the positive and negative don't cancel out. It's basically the L2 norm that will calculate the overall or the average error over the entire mesh that we are solving the equation. And we are going to change the thermal conductivity to represent basically radiation damage. So the degradation of the material property of interest here, the thermal conductivity with radiation. So we'll reduce the thermal conductivity by half and run the simulation again and see how this affect the temperature profile and the average temperature. So let's look at the input file. So now we are going to use the VS Code to look at the input file, read it and modify it, and also run simulation from a terminal inside the VS Code itself. And then once we have the output, then we can use ParaView to visualize the output. So let's go and briefly look at this input file. So this is a very simple input file because we are just solving the heat conduction in 1D. So let's take a look at the input file. So the input file, or one important thing to note that, of course, now if you are on a Windows machine, then you have the WSL and you have Linux and Windows on the same machine. But sometimes we have files on the Windows subsystem, and we want to use like VS Code or ParaView, which we installed on Windows directly. So we wanna make sure that we can basically move or be able to read and open files from or under Linux directly from those Windows applications. So this is now very straightforward because you can use Windows File Explorer. So once you basically have your Linux set up properly, you should have the Linux here appearing and the Linux folders. So basically, you can copy and paste files from Windows to Linux or the other way around. So in my case, I have this input file here. So I wanna put it in a basically under Ubuntu, so in a specific a folder, so we can basically open it and run the input file from this folder under Ubuntu. So are given instructions in or on those slides to do that. So of course, first thing that every time we work with a mouse, we need to activate the mouse environment, right? Because usually we are under the base environment. Here I already activated the mouse environment, but usually this will read base instead of mouse. So you have to activate the mouse environment. And then we are going to basically make a couple of folders to use for different examples. So we're gonna make directory, we're gonna make a folder that we call Ubuntu65. And then inside this folder, so we are going to go inside this folder and basically make another folder, make directory for this specific homework problem. So homework 4. So now we are going to go inside that folder. So it's a homework 4 folder. So right now, of course, it's empty. So if I do ls to list, there is nothing to list. But what we're gonna do is we're gonna move the input file from where it was downloaded in Windows. So this is basically, usually it's gonna be in your download folder, and then move it all the way to this homework folder in Linux. So to do that, simply we are going to use File Explorer, and that's what you are. So what we have done here is those instructions to make those folders inside Linux. So we run everything from a Linux terminal. So I have here my file is somewhere on Windows, and I'm just gonna copy and paste this file into my Ubuntu. So on Ubuntu, it's usually this mouse or this project folder that contain mouse is usually under your username. So this is a project folder, and we are going to that homework 4 folder, right? So it's under the combined module folder that we made and under the Ubuntu65. And this is the homework folder. So now it's empty. I'm just gonna paste this U2 pellet input file. So now the folder, the homework 4 folder is no longer empty. It has the input file. So now I can go to my VS Code and I can basically see if the file is there. Yes, the file is there. So you can see the u2pellet.i. And now we can open this file also from, we can open this file here in VS Code, so we can look at it, read it, and modify it if we need. So we gonna open the file. We can go here directly to homework 4, and then the so this is how the input file look. And again, this is basically the power of the VS Code, that in the same window you can be looking at the input files and editing the input files, and then you can also use a terminal and run this input file. So the input file is simply basically stating the facts and the inputs that we talked about on those slides. So it's a heat conduction problem. We are assuming that we know the surface or the edge temperature, it's 700, and we are using a 4 millimeter pellet radius We are using here SI unit. So this is the length is in terms of meter. And the thermal conductivity, we're assuming it's 5. And we're assuming the value of the heat generation based on the calculation that we know from nuclear engineering. So this is the fission, the energy per fission, and the number of fissions per meter cube per second. So we are using a mesh that is generated inside mousse itself, and this is simply just a cylindrical pellet. It could be hollow or solid, so we are assuming it's a solid, it's not a hollow cylinder. Although that's an example that we can do later, but basically that's why we have this. So there is only one radius, there is no inner and outer radius, there is only one radius there. And then we are solving for the temperature. So this is our variable. So this capital T is for the temperature. And then this is the analytical solution that we talked about. So in order to validate the numerical solution and know that basically we are implementing things correctly, we are going to compare the numerical solution from mousse against the analytical solution, which is an exact solution. Again, this solution is parabolic, has parabolic dependence on the radius, and it scale with heat source and inversely with inversely proportional to the thermal conductivity. Now we define also the thermal conductivity, or the kernel. So this is a little bit of the details of how mousse works. So the kernels, they are basically, those are the terms in the differential equations that we are solving. So we have a diffusion term or a conduction term. So mathematically, diffusion and conduction are the same. So basically, the thermal diffusivity or thermal or mass diffusivity or diffusion coefficients are basically kind of a similar concept in terms of material properties. So we are using a generic diffusion kernel, although basically in our case, conductivity is just simply a constant. And also we are using a heat source kernel. So these are kernels that represent a source term in the differential equation. And this is the heat generated from fission. Then our boundary condition, so it's a differential equation, so we need boundary condition to solve it. So the boundary condition here is a Dirichlet boundary condition, meaning it's a boundary condition on the variable itself that specify the value of the variables that you're solving for, which is in this case the temperature. And this boundary condition is applied at the outer radius, so our maximum, or at the surface. It's a solid, not hollow cylinder, so it's not really, there is no really inner and outer, but basically it is applied at the surface or the edge of this fuel pellet. And then in this case, the thermal conductivity is just constant. In general, this could be a nonlinear problem, meaning the thermal conductivity could be function of temperature, and we can specify this dependence if we want. But for simplicity, to compare with the analytical solution, we're assuming it is simply a constant thermal conductivity. Now, mousse also have a very important feature, which is basically you have a post-processor. So you don't just get the solution of the temperature, you can calculate things based on that solution. So of course, one important calculation of interest would be the average temperature, right? We talked about that the average temperature based on this expected parabolic profile of the temperature should be simply the arithmetic average of the surface temperature and the center line temperature. So we're gonna demonstrate that. And also we are going to look at the error. So we know the analytical solution, and now we are using mousse to calculate the numerical solution. So we're gonna take the difference between those and calculate the L2 error norm. And then also we wanted to know what's the center line temperature. So we know also based on the exact solution, we know the exact value, what it's supposed to be for the center line temperature. It is going to be the maximum temperature in that profile. And we know the exact expression for it, so we can also compare against the analytical expression. Now, a couple of things that are basically related to the software is basically how to solve the equations. So those are differential equations that we solve them. Basically, we discretize them, and if it's nonlinear, in this case, it's actually just simply a linear problem. But basically, we approximate the solution, and eventually, we have a matrix vector multiplications to calculate uh, the derivative, to calculate the solution at each point or each element. So we approximate, that's where the approximation happens, and basically we discretize the equation. So we solve it not for over infinite number of points, we only solve it for a finite domain, and we transform through the discretization, we transform the differential equation into basically multiple algebraic equations at each point, or representing the solution at each point, and then you solve that by you put that in a matrix vector form and solve the matrix vector multiplications. In this case, it's a simple linear problem. So basically, this is and it's also 1D problem. So we're using an exact method or an exact solver. Sorry, a direct solver. However, those details are not very important now if you're new to Moose and finite element. What we need also to know that eventually we are outputting two different types of output. First, this is what would be the name of the output folder, and then the output file. So we have output folder that's called UO2 pellet heat conduction, and the output file will have the same name, but also it will have basically appended to the name at the end the value of the thermal conductivity, so that when we change this value and run another simulation, we will get another output file, so that we get a new output file with each simulation. All the output files though would be located in the same output folder. So we have one folder, but every time we run a new simulation with a new value of the thermal conductivity, we will have a new output files. And we'll have two different types of files. So we have the file where we use ParaView to visualize, so that it's the solution at each element everywhere over the entire pellet. And we have the post-processor file, which is simply a CSV file that we can read or plot using Excel or anything. And the post-processor files has those values. So it's basically whatever you calculate under the post-processor section or block here in a Moose input file, that's what would be output and saved to those basically CSV files. So it will have the average temperature, the average error, and the center line temperature. However, as we will see when we run a Moose input file, those post-processor also will be printed out to the screen while the solution or while the simulation is running. So this is the structure of the input file. What we need to do is basically to just run the Moose simulation. And to do that, there are two ways to run the input file. If you have more than one core, and if you have enabled the MPI in your Ubuntu or Linux terminal, then you can run things in parallel. You can use the MPI, sorry, you can use the MPI execute command and then specify the number of cores. In this case, or this command would be 4, and then you just use Moose optimized. That's the executable, the most executable that we use to run input files, and then -i the input file name. So we will run this command from basically inside this homework folder that we made, since the input file basically stays or lives there. So I'm just gonna use this command, and we know here now inside the homework folder we have the input file is there, so I don't need to give the location or the path to the input file because it is inside this folder where we are right now. So if we just do MPI execute here, I'm using 4 cores. This is really a simple problem, so you don't even need to use many cores. You can even run it in serial without the MPI execute part. But let's do it with 4 cores anyway. Of course, we need to change the input file name to the name of the files that we want to run. So this is going to be UO2. You can hit the tab to autocomplete the name for you and then just enter. So we have an error here. Might be related to the MPI. Let's see. So let's try to run it in serial for now. Hmm. Still- It looks like a mouse error, which is a bit weird. Could be something. Okay, let's try one thing. Which okay. So it could be, so that's another good reminder of why it's not good to copy and paste from files to a terminal. So there could be an extra space or an invisible character that led to that issue. So the command is very simple, right? It's just mouse opt -i and then the input file. So if we run the command, you will see that moose print a few things. So first it print out basically the version of moose, which version we are using and the date and things like that. Uh, how many cores you are using, how many elements you are using, the number of unknowns you are solving for. This related to how many elements you are using and the methods, the solver methods. You can see initially, basically, it assumes the initial guess for all the variables as 0. So initially everything is 0. If things are converging, so the solver is working fine, you will see everything is green here and you will see solve converged at each step. It's a steady state problem, so we only have one step, but you can imagine, of course, if it's a transient time dependent problem, you could be solving for thousands of time steps. But this is a very simple problem. We are looking for the steady state solution, so it's just one solve, one step. You can see here the error is very small, so that means we implemented things correctly and MOS is working properly. The error is small. The difference between the analytical solution and the numerical solution is small. You can see the average temperature is higher than the 700, which is the surface temperature, right? It's about 860. And you can see that the center line temperature, which we know should be the maximum temperature, is a little bit above 1000. And what we can do now is basically, of course, we can visualize things using ParaView, and we're going to do that in a minute. But while we are here, we can also change the value of the thermal conductivity. But before we do that, let's do that first. So we can change the value of the thermal conductivity, so we get all the files that we need first in one shot, and then we visualize them together. So we can kind of indirect way account for radiation effects by assuming that basically the value of the thermal conductivity will decrease after irradiation, which is true towards the end of life of the fuels in the reactor. So we'll assume here it's going to reduce by about one half. Then we are going to save that change. So we made a change to the input file, so we have to save it. Just Control S from here. So now when I run this input file, because of the fact that we are changing the output name, the output file name based on the value of the thermal conductivity, then we will get new output files. But remember, so our maximum temperature here, the center line temperature was about 1000, because we want to see what happens when we reduce the thermal conductivity. So of course, when we reduce the thermal conductivity, that means it is less efficient to conduct heat and more difficult to extract heat. So that means the heat that is generated will stay a bit more inside, and therefore that will drive the temperature up and the temperature gradient. So you would expect that both the center line temperature and the average temperature to increase if we decrease the thermal conductivity. So the center line temperature here is about 1000. So what happens if we run the input file again with a lower value of the thermal conductivity? So again, things work fine. You can see here the center line temperature now is a little bit above more 1300. So it increased by 300 degrees when we reduce the thermal conductivity by one half. So that of course consistent, makes sense, and demonstrates that we implemented things correctly. Now, if we do ls to list the output, you can see now we have one output folder. So if we cd to that folder, now inside that folder, you will see we have four different files. We have the .e and .csv file for each simulation. So we have that for basically a value of thermal conductivity equal 5, and we have that for the value of the thermal conductivity equal 2.5. The CSV files will just have the values of the average temperature and error and center line temperature that we have, that Moose already print out to the screen. But it is this .e file that has the solution everywhere over the mesh, over the entire pellet, and that what we can visualize and look at and examine. And that's what we need ParaView for. So ParaView, after we install it, you can use it to visualize those files, those Exodus, those .e files. So with ParaView, the first time, this is important when you use ParaView for the first time. So because I have used it before, I have under the recent here, I have my Linux or Ubuntu folders. But you can see basically, if it was the first time, ParaView, since it was installed on Windows, it usually only sees the Windows files initially. So to make sure that you will be able to open the files in Linux or under Ubuntu, you just need to know basically the path to your Ubuntu folder. And this path is under wsl.localhost. So basically once you just type that, so you don't have to give the entire path. You can just do ws localhost. Then you can go to Ubuntu. I have two Ubuntu versions, but my mouse is under this one. So it's usually, again, the projects folder is under home username. That's where the combined and the homework folders are. And now this is the new output folder, right? And again, we have those four files for the two simulations. We are going to use the .e files. So let's start with high thermal conductivity value. So initially, depending on the default setting for ParaView, it could give you this basically data sheet, or initially as the first thing that it will read, or the first thing it will render. That's not very important to us for visualization. We wanted to basically use the render view. So we'll make the render view here. And also depending on the default setting, if this eye is not checked by default, you need to check it to basically see the geometry or the mesh that you wanted to see. And now we wanted to look at the variable. So this capital T for the temperature. So this is basically from this drop-down menu. So basically we pick T here, the temperature. Now, usually it will go to the final step. So remember, this is just a one-step steady-state solution, but you could have many time frames if you are solving a transient problem. And also sometimes it will go to the initial step, depending on the default setting of your ParaView. However, you can always make sure that you can basically change from one frame to another. Make sure if you are in the initial zero frame or the frame that has the solution. Sometimes also this map might not be updating correctly. So sometimes basically if you go here at 0 and then go to 1, it doesn't automatically update. So if this happens, you can always make sure that you are updating the color map by clicking this icon here. So this is to rescale to visible data range. So this is our temperature profile. It is maximum at the center line as we expect, and it goes from 1000 to 700. So this is basically by default the surface plot, but if you wanted to, when we talk about finite element and mesh, if you want to see those mesh elements, you can pick this. So this is surface with edges, and then you can basically use your trackpad or mouse to zoom in and zoom out. So those are the finite elements. Those are the elements. That's basically how we are discretizing this entire pellet or domain into specific number of elements. So this is how our elements look like. However, if you don't need to see that, then you just pick surface from here and then you just see the color gradient. Another important thing that you can utilize ParaView for here is to also basically take a line scan or a line plot across this pellet so we can see this parabolic temperature profile, how the temperature change with radius at each radial location along the radius. So you can do that. So there are many icons here that basically have different or show different features and have so ParaView has many capabilities, and you can look at uh, the getting started pages of ParaView. So when you download ParaView, there is a very short getting started document. It's about 3 or 4 pages. You can look at it and read it quickly. But basically, one important feature that we utilize a lot is the plot over line, which will do this. It will basically take a line scan along the radius in this case. So if we hit this plot over line, it will generate this temperature profile with plot over line. Again, sometimes depending on the default setting of your ParaView, sometimes when you just click here, it will apply by default, but sometimes you actually have to hit apply yourself. So if you don't see this profile after you hit plot over line, then it means the default setting is probably not hitting apply by default. So you will have to hit apply here yourself. Now also we can change things on those profiles. So here we have really only one variable, but sometimes there are many variables and you want to just look at one of them at one time. And here actually there is another thing that is basically of no physical relevance, the checked also. So we uncheck this one. So we only need to check the temperature. We're only interested in looking at the temperature. So this is basically how the temperature profile look. We expect it to be highest at the center line, goes to 700 at the boundary, and it has this parabolic shape. So that's correct. What we can do next is also you have the freedom and flexibility here to change a few things. You can basically change the size or the basically the shape of those lines and add a legend or things like that. So you can do that from this properties things. So however, you usually have to activate. So you have to click on basically which profile or which window you are looking at. So you actually update things in that window. And in this case, you will click the temperature variable here, and then you can change things. You can change the line, you can add markers, for example. Let's add circles, can increase the size of lines, so you can make it 5 and things like that. So you have the options to change a few things, and then eventually, as we will see in a minute, you can save all of those things, take screenshots and save those things. But while we're at it here, we can also look at the profile from the other solution. So we visualize the solution for the high thermal conductivity. We can go now to the other .e file with lower thermal conductivity and visualize that. Can open this file. So now you can see there are two files. Again, we have to go and pick the variables that we want to visualize. It's the temperature. Profile is similar, although if you check on a check, you can actually see the difference. So basically, compared so this is the original one with high thermal conductivity. You can see there isn't really high gradient compared to this new file that has lower thermal conductivity. So with lower thermal conductivity, you have basically higher temperature gradient. The temperature goes all the way up to 1300, while for the low case, for the case of low thermal conductivity. But for the original case with high thermal conductivity, the temperature gradient is relatively smaller. It doesn't actually go to 1300, it goes to about just 1000. So we can look at that on the mesh or on the pellet, but also we can use the plot over line again to look at the new parabolic profile for the case of low thermal conductivity, which we know will have higher temperature, higher center line temperature, and also higher temperature gradient overall. So let's do that. So we can also here do another plot over line. So hit this icon. So here it showed on a different profile, but for better visualization, we might want to have both on the same figure. So we can actually do that by clicking on this window that has the first or the original line scan profile. So if we click that and then do the plot over line, it will actually now add the new profile on the same figure. And again, it's because of the fact that in addition to the temperature, it has this element side also checked. We don't want to visualize the element side, we just want to visualize the temperature. So let's uncheck this. So now it's only showing the temperature profiles, and This is for the low thermal conductivity case that is basically given, which is the new one. Remember, the old one was for the high thermal conductivity case, and that's the one that we basically second the line for it. So the new one is for the low thermal conductivity case with this basically a relatively thin line. You can change the thickness, or basically you can make it a give it markers, or basically change the line profile. So if you pick the variable here, temperature for the new one, and let's say make it instead of solid, make it dashed. So that would be the new profile for the low thermal conductivity case, while this is the original profile of the high thermal conductivity case. You can see the profile is self-similar, both are parabolic, so the dependence on radius is the same. Both have the same boundary temperature, right? The 700 degree at the outer. Both are under the same heat generated or heat generation conditions, the same amount of fission or same number of fission and fission energy. But because of the fact that we reduced the thermal conductivity in the second simulation to account for radiation effects, now we have higher center line temperature and we have higher temperature gradient. You can see the gradient is much steeper in the second simulation with lower thermal conductivity. So that's basically what we expect, and we're able to visualize those two different files using ParaView. We're able to look at the entire pellet and look at the basically the spatial dependence or the field solution everywhere on, on the entire pellet, but also we are able to take those line scan and make those line profiles to compare against our prediction and expectation from the analytical solution. Now you can, if you wanted to save that, you can basically go to File here, and then you can save a screenshot. So this is also, of course, ParaView has a lot of capabilities. So if was time dependent and problem and we have many frames, we can even save animations. We can even make a movie out of this simulation. But this is just a steady state problem. So we have only one solution and one frame. And basically we can just save a screenshot here. So basically you can save it, give it a name. Let's just say it's so it's gonna be saved here. So that's also up to you. Where do you want to save it? So maybe you don't want to even save it under the Ubuntu. So it's up to you. You can make any folders. For simplicity now, I'm gonna just leave it in the same folder. Then you can also make whatever format you want. So make it JPEG, you can do that. So it will ask you a little bit about a few things. So the resolution, you can leave it as default, that's fine. The quality, you can increase it all the way to 100% if you want. Um, you can also look at other options if you want. But basically, you can just save it, and then it will save. Usually it will save both of them, but sometimes depending on which window is active, it could just save this window. So make sure if you wanna save just one window, you activate this window, just click on it. Or if you wanna save both of them, so basically you can save It's up to you whether to save just one window or both of them. The default would be to save both of them. So that's basically it. So basically now we know how to run moose input file from a specific folder. We can basically copy and paste that folder from one or that file from one folder to another, especially from Ubuntu to or from Windows to Ubuntu, then run it in Ubuntu using VS Code, get the output, and then basically visualize the output using Purview. All right, so this time we only talked about the thermal performance. So next time we will also talk about the mechanical performance, and then we will couple them and talk about the thermomechanical performance. All right, thank you, and I will see you in the next video.